Case 3. Factors with non-real roots. In a partial fraction problem, we occasionally have a denominator that contains a quadratic factor with non-real roots. For example, x squared plus 4 has factors of x plus 2i and x minus 2i. Rather than breaking this into linear factors that contain i's, we choose to leave this factor as a quadratic in the partial fractions process. This conscious decision not to factor a term completely results in some terms having a more complicated numerator. In this case, every term with an unfactored denominator must have a numerator of degree 1 with 2 unknowns. Consider the following example. For x squared over x to the fourth minus 2x squared minus 8, the factors are an x minus 2, an x plus 2, and an x squared plus 2. We choose not to factor x squared plus 2 further because its factors are x minus I root 2 and x plus I root 2, which are unpleasant. Note that when we set up our fractions, the x minus 2 and the x plus 2 get the standard numerator of a single letter. The degree of the denominators are both degree 1, therefore the numerators must be a lower degree and they must be constants. But in the case of x squared plus 2, because it is degree 2 and we have chosen not to break it up further, it gets the linear numerator of degree 1, in this case a cx plus d. Note also that the degree of the denominator originally was a 4, which tells us we should be looking for 4 letters. In our setup here, you'll note we are indeed looking for 4 letters, A, B, C, and D. Putting the fractions back together and focusing on the numerators, we note that x squared is going to equal a times x plus 2 times the x squared plus 2, b times the x minus 2 and the x squared plus 2, and the cx plus d as a quantity is being multiplied by x minus 2 and x plus 2. Multiplying this all out, we in this case build a system. Dropping the common variable terms in this case to build each equation, we end up with a plus b plus c equaling 0, 2a minus 2b plus d equaling 1, 2a plus 2b minus 4c equaling 0, and 4a minus 4b minus 4d also equaling 0. Since this is a system of 4 equations and 4 unknowns, solving by hand is rather inefficient, so we're going to choose to use technology. In this case, we set up a matrix with 4 rows and 5 columns. The first column contains the A coefficients, the second column contains the B coefficients, the third column contains the C coefficients, the fourth column contains the D coefficients, and the last column contains the constants from the right-hand sides of all the equations. We can now use technology to use reduced row echelon form and solve this, and we end up with a matrix with 1/6, negative 1/6, 0, and 1/3 in the far right column. That tells us that A is 1/6, B is negative 1/6, C is 0, and D is 1/3. Going back to our original partial fraction breakup, we can now plug those values in. Note that we originally expected to have a C value. We do, it's 0, but we can simplify the equation down so that it's simply 1/6 over x minus 2, a negative 1/6 over x plus 2, and a 1/3 over x squared plus 2. Now let's consider a slightly more complicated example that brings case 2 into the mix. For x squared plus 1 to the third power in this denominator, we're going to need 3 fractions. 1 fraction for each power of this repeated factor of x squared plus 1. Note, though, that since the first fraction has a denominator of x squared plus 1, that gets the degree 1 numerator. All the other fractions with the same x squared plus 1 in the denominator, although to higher powers, also get the same type of degree 1 numerator of cx plus d and ex plus f. Note again, the degree of the original denominator was degree 6, and we're looking for 6 letters, a, b, c, d, e, and f. Again, we're going to put the fractions back together and focus on the numerators. Multiplying it all out, we again see that we're building a system. But in this case, this might be a system that we can solve by hand. We already know that A is 0. We already know that B is 1. So we're going to consider this both by hand and by technology to show that the result is the same. Since a is 0 and b is 1, let's start by plugging those values into the other equations. When we do that, we quickly realize that c is 0 and d is 0. Plugging in the values for c and d into the remaining two equations, we're able to find out that e is 4 and that f is 0. Using technology, we would do it the same way we did in the first example. We would build a matrix. In this case, it has 6 rows and 7 columns. Definitely a technology-based matrix. Using reduced row echelon form on our calculator or computer, we would end up with a last column of 0, 1, 0, 0, 4, and 0, which corresponds to the values we obtained by hand, that a is 0, b is 1, c is 0, d is 0, e is 4, and f is 0. Again, we can plug back into the original partial fraction decomposition, and we end up with just 2 fractions. Since the middle fraction, both c and d were 0, that fraction turns out to be unnecessary in this case. Some concluding thoughts. If a factor of the denominator has non-real roots in a partial fractions problem, stop at the quadratic factor with the non-real roots. Give each partial fraction with that quadratic factor in the denominator a numerator of the form ax plus b, a degree 1. Expect to solve the system in this case may require technology and matrices to solve efficiently. Thank you.